This is the videotape lecture for elementary statistics, the Wednesday class I'm missing due to surgery. This is on the normal distribution. This is chapter 6. In Mann's book. Okay, so at the end of Monday's class we had talked about discrete random variables. The normal distribution is an example of a distribution that's modeled to used to model continuous random variables. And visually, most of you already know the normal distribution from somewhere else in your life. It's more commonly referred to as the bell curve. Now, the way things work with continuous distributions, some things are the same, others are different. One thing that is the same here is that this horizontal axis is our axis for our variable. But when you talk about a normal distribution, instead of having individual pieces of mass at different points, essentially what we've got is probability mass spread out over some interval on the x-axis. In the case of the bell curve, this technically goes from negative infinity to positive infinity. And some basic properties here. First off, the probability of falling in a specific interval is equal to the area under the curve and over the specified interval. So let's say that we have a point A here and a point B here, and we're interested in the probability that x is between A and B. Then this probability corresponds to that area right there. Now, because probability corresponds to area, there's certain things that must be true. First off, total area under curve has to equal 1. So if we were to shade everything here, going out all the way in both directions, then this area would be equal to 1. So then, what is the height telling us? Because in this type of setting, height is not equal to probability. But what height does for us is that the height gives us a notion of how likely a certain interval is compared to another interval. So I'll draw one of these bell curves again. And if we take an interval of a certain width, and what I'll do here is I'll use my eraser to give myself a certain width. Let's say we're looking at that interval right there, as opposed to that same width interval right here. The fact that this curve is so much higher here basically entails or implies that we're going to have a lot more area in this region than we will right there. So that's telling us that the probability of falling somewhere in this interval is going to be much larger than the probability of falling somewhere in this interval. Now, one other thing that's a little different from what we did with the discrete random variables. Suppose that in the previous case, we had looked at the probability that x fell between a and b, where we include a and b in those endpoints. In this situation, suppose that what we're doing is looking for the probability that x is between a and b, but in this case, we don't include a in our endpoints. So let's say that a is right here and b is right here. We're including b, so we're going to have a solid line right there, but at a, we're not including it, so we're going to have a dashed line right there. And we're still looking at the area in between. So the question then becomes, well, how does this area relate to that area right there? And the fact of the matter is that the only difference between this region and the region we had drawn over here is that we got rid of this line. So when we think about things in terms of area, we need two dimensions to be able to calculate area. And as far as this is concerned, any line, I'm doing vertical lines here, any line has only one dimension. There is no width to this line, it's just going up. So effectively, these two probabilities are the same. So what we have here is for any continuous random variable, not just the normal distribution, but other continuous random variables that we'll talk about before the course is over. The probability that a is less than x is less than or equal to b is the same as the probability that a is less than x, which is less than b, which is equal to the probability that a is less than or equal to x, which is less than b, which is equal to the probability that a is less than or equal to x, which is less than or equal to b. So in short, the or equals, whenever you're working with a continuous random variable, make no difference in terms of the probability calculations. You're going to enter the same endpoints whether you're talking about a situation where you have an or equal to case or whether you don't have an or equal to case. Okay. So now, for some more specific stuff about a normal distribution, as the shape shows or identifies here, normal distribution is symmetric. And at this point in the course, we've done enough with symmetric distributions that we know that if something is symmetric, then the mean is going to fall visually right in the middle. So right here, we have the mean of the distribution, mu. And let's draw a line, dot it right there for something else we're going to see. Well, we've got the mean, and we've been talking about standard deviations enough at this point. So as far as this curve is concerned, what does a standard deviation amount to? Well, the way to think about this is, and here's my fun analogy for this one. Imagine this as being a roller coaster. So, you're on the train, it hooks up to the chain, and you're getting pulled up the hill. and you get up towards the top of the hill, and once the train hits the top of the hill, in order for the roller coaster to be any fun at all, then the hill's got to start going down. And not only does it have to start going down, but in order to be fun, it's got to get steeper. If that thing doesn't get steeper, you go over the top, you go, ah! Yeah. Well, anyway, so it's got to start getting steeper. And it does that for a while, and you're having fun, and you know, who knows what's flying past you. But at some point down the line here, in order to avoid serious pain, the hill's got to stop getting steeper and start getting flatter. And there is a point that this happens on in this curve. And if you were to visually locate it and draw a horizontal line over, and I realize now that I've drawn this, I should have gotten in the way of the camera to have this centered better. That's a little bit better. This distance right here is sigma. That's one standard deviation. And if you go in this direction, that's also one standard deviation. So this point right here, we've gone from mu to mu plus sigma. We go out the same distance here, we're at mu plus 2 sigma. And we go out one more time, and we're at mu plus 3 sigma. On the other side, going out 1, 2, and 3 standard deviations, we're at mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. So before we even talk about what those different regions mean, let's just put some numbers in here and have an example. Let's say that we've got a normal distribution that you're told that the mean is 10 and that the standard deviation is 2. So when we talk about these points right here and the values of x that correspond to these various points, this is 10 right here, and each time we go out one jump, we're taking a jump of 2 units. So this would be 12, this would be 14, and that would be 16. And in this direction, you'd have 8, 6, and 4. Now, a couple other things to note here. I did say that this curve goes out infinitely, toward to negative infinity in this direction, positive infinity in this direction. But one of the things to notice here is that by the time we get out to 3 standard deviations below or above the mean, and you know, I've been drawing these now since 1989, and I still can't do a great job of it. So, you know, as far as the art's concerned, as long as you do a decent job of it, I'll be fine. Just please don't do this. That is not a bell curve. That's a sunset, possibly. It may be a derby. You know, it could be half a cantaloupe sitting on a counter, but it's not a bell curve. You've got to make sure that this is bell-shaped. But by the time you get out here, there's very, very little left to work with. So most of the stuff in a normal distribution is going to fall within 3 standard deviations of the mean. So, the next thing that we can get a little bit more specific about a normal distribution with is something called the empirical rule. And again, we'll do this visually here. Wow, that's lousy. It's the problem of doing things semi-live when you've only got a 2 gig chip to record on. So let's see if I can do a little bit better here. Wow, I think I got some editing to do. Okay, well, anyway, like I said, we've got our mean here, and let's say right here, this is mu minus sigma, and right here is in the neighborhood of mu plus sigma. This region right here has an area that's approximately 0.68. So what that means is that in any normal distribution, approximately 68% of the observations fall in the interval mu minus sigma to mu plus sigma. There are also percentages associated with mu minus 2 sigma to mu plus 2 sigma. So now we're taking this interval. We're taking the 68% we originally had, and we're going to add on that much right there, and that much right there. Well, it turns out that if you look at the interval mu minus 2 sigma to mu plus 2 sigma, this contains approximately 95% of all observations. And since it contains approximately 95%, one thing to recognize here, how much did we add? Well, we've got 95 now. We started with 68. So 95 minus 68 is 27. And we added the same amount on each side. So we split up this 27 in half. So this part I just shaded amounts to approximately 0.135 or 13.5%, and the same for this. Now, for 3 standard deviations, we're now adding on that region right there, and this region right there. And for that interval, the approximate percentage is 99.7%. So in this case, we've gone from 95 to 99.7. We've added an additional 4.7% total. So on each side, we've added half of that. Half of that is 2.35%. So each one of these is 0.0235 approximately. And what's left over out in the tails here is this 0.3%. We split that evenly, it's 0.15%. So each one of these is approximately 0.0015. So it doesn't matter what the mean and the standard deviation are. For any normal distribution, this is the approximate breakup, or breakdown, I should say, of how the data are distributed. Now, we're going to be using our calculators and functions on our calculators to get the actual probabilities, but one nice thing about knowing the empirical rule is if you know these percentages, you can get an idea as to whether or not you've made a mistake in punching something into your calculator, because you should be able to get at least somewhat of an idea of what your answer should be ahead of time. Okay, so we're going to take a problem out of the book and just demonstrate this with some numbers. Okay, the numbers that we're using for this problem are on page 283. Sorry, page 200 at the bottom, my goof. And problem 61, it says, according to the records of an electric company serving the Boston area, the mean electricity consumption during winter for all households is 1,650 kilowatt hours per month. So we have mu is equal to 1,650 kilowatt hours. And the standard deviation of 320 kilowatt hours. So I'll draw my bell curve here and hopefully do a lot better than I did last time. Not so much for hoping. Not too bad. So our mean right here is 1,650. And if we go 1, 2, and 3 standard deviations out on each side, again, each one of these jumps is 1 standard deviation or 320 kilowatt hours. So each time I'm going to add an additional 320 to the right, and I'm going to subtract 320 for each jump I go to the left. Remember, our variable here is x, so this is energy usage monthly. So if we add 320, at this point we're at 1970. Another 320 puts us at 2290. And another 320 will give us 2,610. In the opposite direction, 1330, 1,010, and 690. So, using the empirical rule here, if the question were asked, what are the endpoints of the interval containing the middle 95% of all energy usage amounts the empirical rule says that the middle 95% is covered over 2 standard deviations above and below the mean. So the interval in this case would be from 1,010 to 2,290. Now we'll take a different approach, and let's say that we were to give the endpoints of an interval here. So let's say that we're interested in the interval from 1,330 to 2,610. And we're interested in what percentage falls in this interval. So There are a number of ways you can do this, but if you go back and look at the diagram that we drew with the different percentages put in here, we know from one standard deviation below the mean to one standard deviation above the mean, that's this part right here, that amounted to the middle approximately 68%. From 1970 to 2290, we tacked on another 0.135 approximately, and from 2290 to 2610, we tacked on an additional 0.0235. So if you add all of those together, what you're going to get is 0.8385, and so the percentage associated with this is approximately 83.85%. Okay, so what we have remaining to do with this, at least as far as this video is concerned, is take a look at how to handle situations that don't match up with the empirical rule, or I should say the more general situation, because we're not just interested in 1, 2, or 3 standard deviations away from the mean. We're interested in quite a wide variety here. So we'll use these same numbers in terms of the distribution. So again, our mean here was, sorry, I've zoned for a moment, 1650. And our standard deviation was 320. So here's the type of question you might see. So suppose we had, what is the probability that a randomly selected customer has a power bill exceeding 1,500 kilowatt hours a month. Using our random variable notation, we're looking for the probability that x is greater than 1,500. If we want to put this on the graph, again, we can get an idea of where this falls on the graph because one standard deviation is 320. So as we drew this before, right here, this is at 1330. 1,500 is just a tiny bit closer to 1650 than it is to 1,300. So 1,500 may be right about here. And because we're working with a strictly greater than inequality as opposed to throwing in an or equal, we'll have a dashed line up here. And we want the area to the right. Which is right there. So first off, before we go to the calculator here, well, what does the empirical rule tell us? Well, even without the empirical rule, we know this is symmetric. It's split at 1650, and we've got a little bit more than half of this. So we know that this answer right here has to be more than a half. Similarly, if we use the empirical rule, if we go one standard deviation over to the left, this from 1650 to the right is 50% of the area under the curve, and this interval right here would add an additional 34%. We're not adding all of it, but adding 34% to 50% would give us 84%, so we know that this has to be less than 0.84. So, how are we going to go about doing this with the calculator? So before we actually pull that out, for those of you with the TI-89s, what you're going to do is you're going to go to that same stat list editor function that you used to get to where you entered data earlier on in the course. Once you type in the stat list editor and you start seeing the lists, you're going to want to press the F5 button, which is the distribution button. Those of you with the TI-83s and 84s, there's a distribution button on your calculator. The way you get to it is by pressing the second button and then pressing the VARS button. The VARS button is just below the down arrow. Now, in both cases, once you get to this point, what you're going to want to do is pick the function normal CDF. There's a function that comes before it in the list called normal PDF. We are never going to use that normal PDF function in this class. We're going to use the normal CDF, and when I get back next week, we're also going to use the inverse normal function. So as far as this is concerned, certain things you need to enter in with the normal CDF. There's 4 things. You need to enter the lower endpoint of your interval. You need to enter the upper endpoint. You need to enter the value of mu, and you need to enter the value of sigma. Those of you with 89s know at this point you get dialog boxes, and these will be the 4 things you enter in the different parts of the dialog box. For those of you who have an 83 or an 84, essentially what's going to happen is after you call this function, you're going to get an open parenthesis, and you're going to need to enter these 4 items separated by commas. So, as you'll see on the calculator in a moment, for the purpose of this problem, what you will do is call up that normal CDF function. Our lower endpoint of this interval is 1500. We don't have an upper endpoint here. Effectively, we're letting this go on infinitely, even though we know we can't have infinite power usage for the purpose of modeling. That's what we're using. So if you have a TI-89, there is actually an infinity button on your TI-89. If you have no upper endpoint, you will put infinity there for the upper endpoint. If you have no lower endpoint, you will put negative infinity for the lower endpoint. For the 83s and 84s, there are a number of different ways that we can handle this. One of the standard ways is for positive infinity, we are going to type in E99. I'll show you how to do that with the calculator in just a moment. But this represents 10 to the 99th power. It's not infinity, it's a finite number, but for our purposes, it's certainly large enough that unless we're doing something with celestial mechanics, which we're certainly not doing in this course, we don't have to worry about this. If you don't have a lower endpoint, in place of typing in negative infinity, you would type in negative E99. So what we're going to do here is we're going to put in E99, and I'll show you how to do that in a moment, and then the mean, so that's 1650, one more comma, the standard deviation, that's 320. So I'll go to the calculator and show you how to do this now. Pardon the bobble for a moment. I've got to detach this and then put it over the calculator so you can see this. And recognize that I've got about 14 minutes left on this video, so we're good in terms of time. Hopefully you're not getting dizzy as I do this. Let's see how we do here. Okay, so what I've got here is the TI-83, and so that you can notice here as I zoom in, I said just below the down arrow is the distribution key. It's right there. Okay, and so we've got the calculator on right now, and I said to hit the second and distribution. So there's the second, and then we'll go over here and hit the vars key. This is fun trying to do this with a camera over it. And we have this menu right here. And as you can see, the normal CDF function is item number 2. This menu may look a little bit different depending upon which calculator you've got. Items 1, 2, and 3 won't look different for anybody with an 83 or an 84. But the functions may change once you hit item 4. It will look a little bit different for those of you with an 89, but again, we just need to choose the normal CDF function. Okay, so we have that function right there. As I said, the lower endpoint is 1330, so I know you know how to hit those numbers, so I'll just go ahead and type those in. The next thing we're going to do is put in a comma. If you've forgotten, the comma is right there. It's the second, it's the button right above the 7. So we'll put that comma in. Okay. The next thing we need to do is put in E99. Now, the way that we get E99, the E appears when we actually hit the double E button. And you'll notice the double E button is the second function for the comma. Okay. It says double E above it, but when we type it in, only a single E appears. So we'll hit second function, and then we'll hit the double E. And as I said, we're going to get a single E on the calculator. Okay. We need to type 99, a comma, the mean which was 1,000. Oh, I made a mistake here. I'm sorry, but let's go back and fix this. We can always edit. I said the lower limit was 1330, and that's my fault. This should be 1500, so I'll just go type over that. Okay. The mean was 1,650. And we've got one more comma, followed by the standard deviation, 320. We'll hit the parenthesis and hit enter. And as you can see, our value there is 0.680376 if we round that to 6 decimal places. So let me put this camera back on and go back to the board for a moment. So this region right here, this area, is 0.680376. And so that is the probability that we're interested in, probability that x is greater than 1500. So basically what we're finding out here is that about 68% of the households having monthly power usage in the Boston area during the winter of more than 1,500 kilowatt hours. Okay. So that's a greater than case. We're going to do 2 more of these. Here's our curve again. So here's 1650. And in this case, let's say we're looking for the probability that x is less than 1,000. So we're talking about some pretty low power usage. If we mark off 1, 2, and 3 standard deviations, we said before this is going to be 1330, this is going to be 1010, and this is going to be 690. So 1,000 is right about here, and we're interested in that region right there. So visually, you can see that this is going to be pretty small. We know that outside 2 standard deviations, inside 2 standard deviations, we had approximately 95%. So outside them, we have approximately 5%, and we split that evenly. So we know from 1010 and below, it's approximately 2.5%, or a probability of approximately 0.025. We haven't quite filled that region, so this probability is going to be a little bit smaller. So again, using the normal CDF function, what we're going to do, we do not have a lower endpoint, so this is going to be negative E99. For those of you with 89s, it's going to be negative infinity, comma, 1,000, the mean, which is 1650, and the standard deviation, which is 320. Okay, so, sorry for the cord there. Let's call this function again. So remember, it's second, and then the vars button. There's our menu again. So we'll scroll down to normal CDF and hit enter, or we could just press the 2 button. Now we need negative E99. When you're doing the negative, don't hit the subtraction key. Make sure you hit the minus key, which is right here next to the decimal. Then we're going to go second and hit the double E key. And there's our single E on the screen. We'll type 99, put in a comma. Our upper endpoint was 1,000. So there's 1,000. Comma, put the mean in. The mean was 1650. And one more comma, 320. And remember I said this was going to be approximately a little bit less than 0.025. And as you can see, it's 0.02111. So approximately 2.11% of all of these households have a monthly energy usage during the winter of less than 1,000 kilowatt hours. Okay. Well, I've only got about 4 minutes left on this, so I'm going to go ahead and finish up this with one more example without putting this back on the board. For now, I'll write it up afterwards. So for this last case, what we're going to do is we're going to do the probability that the monthly energy usage is anywhere between 1,200 and 1,400 kilowatt hours. In this case, we have both a lower and an upper endpoint, so we don't have to worry about the E99. We'll just call the function again, second distribution, and call the normal CDF. Our low endpoint is 1200, comma, our upper endpoint is 1400, a comma. Our mean is 1650, and the standard deviation is 320. If we enter that in, that's 0.1375, so about 13.75% of the households have monthly power usage in that 1200 to 1400 range. We'll go ahead and draw this picture up on the board so you can see what I was talking about. First off, in order to finish up this previous one, this region right here is 0.02111. Now, 1200 to 1400. 1200 is going to be right about here, and 1400 is going to be right about here. So as far as that region is concerned, the probability that X is between 1200 and 1400 is equal to 0.1375. And that is that area right there. We still have some more to do with the normal distribution when I get back, but as far as homework is concerned, for between now and the next class, the homework problems to look at are on pages 194 and 195. You do have the list in this for homework, but it's problems 6.38, 6.43, 6.44, and 6.49. And if you have any questions, we'll handle things next week when I'm back. Have a good rest of the week, and I'll see you soon.